So this is problem 23. So we have like multi-stage amplifiers. So in this particular circuit, we have amplifier 1. Okay, then we have at the output of that amplifier 1, we have a second amplifier connected, and then we have our load. Okay, so we have two amplifiers cascaded. For this circuit, we know that AV1 and AV2 is equals to 100, and then we have some conditions, okay, to calculate the output voltage. Okay, so before we analyze the circuit using values like AV1, AV2, or RL, like 100K and AV1 and AV2 100, let's get the the voltage transfer function like V out over Vs to basically uh, to 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 give like a general form, so we can just substitute the values that we have here in ABC, and then we can just like easily calculate that. So let's analyze the circuit, which is kind of similar to the analysis that we have done on the previous problems, okay? But it's just that now we have like one more stage before we get to the output, okay? So let's start with VI1, right? This voltage right here. So VI1, it's just the voltage divider between RS and RI1, right? So it's VS times RI1 divided by RI1 plus RS, right? Now, VI2, it's again another voltage divider, right? Between between AV1, VI1, right? It's a voltage divider between Rout1 and Ri2. So VI2 is equals to AV1 times VI1 times Ri2 divided by Ri1, sorry, not Ri, it's the output resistance. So it's Rout1 plus Ri2, right? That's VA2. And what's V out on this stage here? It's just another voltage divider between RL2 and RL. And the input voltage is AV2 times VI1. So in this case, if we just go to the right, V out is equals to AV2 times VI2 times RL divided by RL plus R out 2. Okay. Now, if we look at these equations, okay, we can just back substitute. So we know that VI1 here is this term here, and we know that VI2 is this term here, along with this one substituted in VI1. So it's just a matter of like several multiplications, like a series of multiplications. So V out is going to be equals to, so in this case, if we substitute VI1 as Vs plus times R01, we get, and then substitute VI2, we get something that is AV1 times AV2 times RI1 from this equation here times RI2 from this equation here times RL from this equation here divided by Ri1 plus Rs from this equation times Rout1 plus Ri1 from this equation here times RL plus Rout2 from this equation here. And that's also times Vs, right? So if we just take this Vs here and put it divided by, and put it like this. Well, let's keep it here because it's just asking for V out, so let's times Vs. So that's the equation that we have for the output voltage. And now for each one of the cases at part A, B, and C, it's just a matter of substituting the values of resistance and the voltage and gains here in this equation to get the value of V out. Okay, so for part A, if we substitute the values of the resistor, we get a voltage V out that's equals to 9.999 volts. And what's the characteristics of this? Basically, the condition of this case is that our input resistance R1. So the main thing here is that our input resistance R1 and Ri2, they are approximately infinite. So they are very high, right? For part B, the output voltage is equals to 8.91. Now see that we have decreased the voltage at the output for the same 1 millivolt at the input. And what's the difference now? The difference is that, besides the value of the source resistance, is that the input resistance is equals to the input resistance 2, which is equals now to 1K. So we have a finite value for R1 for the input resistances. And for part C, uh, we have the same condition for the input resistance at part B, but now V out is equals to 1.25 volts and the source resistance is equals to 1K ohm. So let me just write. So in this case here, let me put this. So Rs here is equals to 1K. Rs here is equals to 100. And here Ri1 equals to Ri2 equals to 1K. And Rs is equals to 1K again. So what do you observe here? If the input resistance is equals to a very high value, the voltage at the output, it basically gets multiplied by the gains here, AV1 and AV2, right? So we go from 1 milli to almost 10 volts, which is equals to 10,000 times the value of the input voltage. But what happens if if remember that we have applied voltage divider in this case here and in this case here. So that's basically the final answer, right, for part 1 and 2 of the last question. What happens to the amplifier like with the gain, and what would be like with the output voltage in respect to Rs and Ri and Rout and Rl? So for part 1, what's going on with Rs and Ri is that basically if we have like a infinite or a very high input resistance, most of the voltage, the input voltage, will be dropped across this voltage, this resistor here and this resistor here. So we get maximum voltage being transferred to these voltage sources here, these dependent voltage sources, which leads to a higher voltage being provided to the output here, right? So disregard our out in this case. Now, if Ri becomes finite and Rs is very high, we start to have more voltage being dropped across Rs. So we are basically losing like power, dissipating heat in this source resistance, right? So if this source resistance becomes large and this Ri1 here becomes smaller or at the same order of Rs, we start to reduce the voltage that's being dropped across Ri1, and then once we use that voltage to calculate this new voltage on a second stage, we reduce that. Okay, so basically for the first question here, we must have an Ri that's very high and Rs that it's small as possible. Okay, so the small, it should be the it should be almost zero, as much the smallest as possible. So for part 2, what about the output resistance and RL? So basically the thing here is that if we want the voltage AV2 V12 here to be applied fully to RL, this output resistance or this output resistance here it should be smallest as possible. So ideally, in an ideal amplifier, that output resistance should be 0. Okay? So that's it for this problem.